Now we're going to look at an example of a problem that we will first analyze from a dynamic programming point of view, and then we'll find that we can take a greedy algorithms approach. This will show the relationship between the two while also illustrating greedy algorithms. In the activity scheduling problem, we will assume that there is a single resource with mutually exclusive access to it. Contending for this resource is a set S of activities. We're going to call them A1 through AN. Each of these activities, A sub I, starts at S of I and finishes at F of I, or before F of I, so that it's going to be within this interval. This is so that we can have them butt up against each other, open-ended interval there. We're going to assume that the set is sorted by their finishing time. And the optimization problem here is to select the largest set of non-overlapping activities, or mutually compatible activities from S. For example, here's a set of activities, A sub I. So activity 1 starts at time 1, finishes by time 3. Activity 2 starts at time 2, finishes by time 3. That overlaps with activity 1, so they can't both run at the same time. 3 starts at 4, finishes at 7. That could follow activity 1, and so on. So we want to pick the maximal set out of here of mutually compatible activities. And here's a graphical representation of this set of activities. When we display it visually like this, the human visual system can, of course, fairly quickly pick out possible solutions. For example, here we have 4 activities that do not overlap with each other, and we could swap A9 for A8. But when you've got a lot of activities and you're not dealing with a visualization, you're dealing with a data structure. Of course, we need a computer to figure out what the optimal solution is. So let's look at the structure of this problem from a dynamic programming perspective. So a dynamic programming approach characterizes the choices to be made, assumes that you can make an optimal choice, and then considers, given that you've made the optimal choice at the top level, how must the problem break down recursively to include optimal solutions to subproblems. And when you do this, you want to do it in a general way that applies to both the original problem and the subproblems. As we break down the problem, we might be looking at constrained time intervals. So we might have to look at a time interval between I and j. So then we're going to define the set ij to be the set of all activities that fit within this interval. And so we're going to treat it as if there was an activity already scheduled, A sub I, and another scheduled A sub j. And so A sub I is a starting one and A sub j is the finishing one. And so we're going to say the set of all the activities left to consider within this interval is all A sub k in the total set of activities here, such that the finishing time, such that it starts after this I finishing time. So start of k is after the finishing time, and then the finishing time for k is before or equal to the start time of the other bounding activity on the upper end, S of j. So this is the set of activities to consider. Diagrammatically, we can think that at some point we have an activity I, and at some point in the future, possibly other stuff following, we have an activity j. And so this is the finishing time for I, this is the start time for j, and we want to consider in this interval all A sub k that fit in here. Its start and its finish are in between these two. And there could be, of course, many things that meet this definition, other ones in here that meet this definition. So now let's assume we've got an optimal solution to this subproblem here. And we're going to call the set of activities that constitute this optimal solution Aij. So that's a set of activities chosen out of this set here. And we're going to assume that some activity AK is part of this, that this was the one chosen out of this set. And then we're going to look at the recursive structure of the problem that remains. Well, you can see pretty quickly, if we chose AK out of this set, the recursive remaining problems are going to be this one and this one, right? So let's write that out. Maybe I'll draw like this. the candidate set activities for these subproblems would be SIK, going from I to activity K, and SKJ, going from activity K to activity J. So we're going to call the optimal solution to this subproblem SIK. AIK will be the solution, and the optimal solution to this subset, selecting out of all the activities in here, the ones that the maximum number we can have, AKJ. And so now we can ask, what's the recursive structure of this overall problem, its solution? Well, it consists of this set of activities union with the one we chose here, union with this set here. Now, if you remember the binary search tree dynamic programming problem that I discussed in the previous topic, did something similar. It looked at picking the root of a tree and then solving the subtree for each side and then putting it all together. So this is sort of a similar binary breaking things down. And of course, this being dynamic programming, we don't know which AK is the best one. Eventually, we're going to see some recursive equations in code that iterate over all the possible A sub k's and then pick the one with the the best cost function, which actually is going to be maximizing the number of activities. So the number of activities that we get, this is the value of the solution, is going to be just the size of these sets, right? And we'll say plus 1 plus the size of this set. Now, by the cut and paste argument, an optimal solution for Sij, which is we've defined to be Aij, must include the optimal solution for these two things here. So these two things must be optimal, because if they weren't, by a cut and paste argument, we could go cut this out, paste back in a set that had one more or two more, had more activities, and then we would get a better, since we were just adding up the sizes of the set, then we would get a better global solution. So that would contradict the assumption that the global solution is optimal. Therefore, this displays optimal substructure, and this can lead us directly to a recursive solution. So far, through this diagram and this reasoning, we have characterized the structure of an optimal solution. It looks like this. We've shown that it has optimal substructure. Next, we need to recursively define the value of an optimal solution. We've got the beginnings of it here. We're going to do that next with a recursive formula. And then after that, we will show how to compute the value of an optimal solution, the third step of dynamic programming analysis, and then how to construct an optimal solution from computed information. But before we get to that third and fourth step, we're going to discover something about this problem that leads us to take a greedy approach. So let's look at what they use C for cost. This is actually the value of an optimal solution. Okay, this is actually the same thing as this size of the set Aij, but now we're switching to the usual dynamic programming notation here. So the cost or value of an optimal solution, let's say it's going to be 0 if Sij is the null set, if it's empty. And otherwise, what will its value be? Well, here's an equation for a particular choice of A sub k was the one that we split it by. Remember, we assume that at the outset, we assume that we can make the optimal analysis, the optimal choice, and then we analyze the substructure assuming we have made the optimal choice. But now we have to dispense with that assumption that we don't know what the optimal choice is. So as usual, we do basically a search. We try all possibilities. We check all AK in the set of options, Sij. So we're going to look for the maximum such that this value is maximized. And this is the recursive part. Cik, that's for this thing here, plus Ckj, that's for this thing here, plus 1. And this, of course, is for if Sij is not null. So that is our recursive definition of the value of an optimal solution. And then from this, we could write a recursive algorithm that we memorize, or we could, develop an iterative algorithm that fills in tables. You could figure out what order to do it in, solve the subproblems, fill in tables for these. So when we do this search at this level, we don't have to recompute those. We can just look them up. But it turns out that we don't have to do all of that because this problem has a particular property. And that property, which we'll prove, is the greedy choice property. Let's make an observation here. If we always pick the activity starting at the beginning because they are sorted, if we pick the activity that finishes first, so that's always going to be a sub 1, and then recursively solve the subproblem of the rest, so a sub 2 would be the beginning of the subproblem, then the intuition is by choosing the activity that finishes first, we're leaving the most room for all the remaining activities. And one thing that this does is that it breaks, it changes this from a problem that has two subproblems to one that has only one subproblem. So this notation here is too complex. We're going to switch to a simpler notation. We're going to say we're just going to pick off the next activity and then solve the subproblem of all the remaining activities. So let's rewrite this for that approach. This is kind of like what we did with cut rod. At first we were dividing things up in different places, and then we realized we could just pick it off from the beginning. So now we're going to redefine the set of available choices, S of k, to be all the activities in S, AI in S, such that the start time of the activity is greater than or equal to the finish time of activity k. But of course we're always going to pick the first one. So we could actually just write our code that just pick a sub 1 and set k equals 1 and then look at the remainder. So after choosing a sub 1, we have, we have to solve s sub 1. And then later on we might choose some other. Then we have to solve s sub k, and so on. Of course, that's what we've written up here. So by optimal substructure, which we've already shown, if one of these items, a sub 1 or a sub k, is part of an optimal solution, then the optimal solution to the original problem consists of that choice plus all the activities in this set, which are the remaining items that are available. We do have to prove that a sub 1 is always part of some optimal solution. And if we do this, of course, recursively, once we take a sub 1 out, this will apply to all the other ones that then become the first item in the list. We're going to write out a theorem. So this is a greedy choice theorem for this problem, saying if we have a non-empty set, S sub k, of activities to consider, and a sub m has the earliest finish time in S sub k, then a sub m is included in some optimal solution. So that means we are safe in picking the item with the earliest finish time in S sub k, because it will be possible to construct an optimal solution from it. It doesn't necessarily mean that it's the only choice that leads to an optimal solution, but it's a safe choice, and the nice thing about greedy algorithms is you don't have to search, you just make the locally optimal choice, like just picking that fruit in front of you. We do this with a cut and paste argument, but rather than deriving a contradiction, we show that we can construct an optimal solution that will include a sub n. So let's start by letting a sub k be an optimal solution to s sub k, and we're also going to pick out the element a sub j in a sub k, the solution that has the earliest finish time. Okay, so first of all, of course, if j equals m, we are done, because we have just shown that there is an optimal solution with a sub m in it. So the difficult part, of course, is when they're not equal to, when there's some other item, a sub j is in the optimal solution. Well, we can just do a cut and paste construction. So otherwise, we're going to do this. We're going to construct a new optimal solution, a prime sub k, which is going to consist of the original optimal solution minus a sub j, but replacing it with a sub m. So we have to show that this is indeed a legal solution. Well, the activities in a k were disjoint because it was a solution. Since a sub j was the first activity to finish, and by our hypothesis, the a sub k has the earliest finish time in s sub k, so this one can't finish later than a sub j, and a sub m cannot overlap with any other activities in a prime sub of k, so it's got to be legal to do this substitution here. It's got to work. And we didn't make any other changes. And also, the size of the two sets are the same. We took one out, we put one in, so the cost or value of the solutions are the same. So therefore, this must also be an optimal solution to S of k that includes now A sub n. So this is a proof that the activity scheduling problem has the greedy choice property, and we don't need the full power of dynamic programming. We can just keep greedily choosing the activity that finishes first, and then continue through ignoring any activities that are incompatible with it until you get another one that is the earliest finisher in the remaining set, and just keep repeating that until you get to the end. So let's look at an algorithm that actually solves this problem using the greedy strategy. The CLRS text defines a recursive activity selector and then discusses how it's tail recursive and converts it into this iterative one. We'll just go right to this iterative one here. So we've seen that we know that the very first element, A sub 1, will always be part of a solution under the greedy choice algorithm because it's sorted by finish times, and that leaves the most time left for other activities to be scheduled. So we're going to initialize, first of all, n to be the length of this list so we can control our loop, and then our set A will be the initialized to the first activity. And with k is 1, indicating that activity 1 has been selected. You may remember in all the analyses, this is our A sub k. So we're, at first we thought about bounding both sides of it, but then we discovered we don't have to do that. We do the kind of like we did with the cut rod. We just chip off the thing at the front, the next activity, and then we only have to solve the sub-problem of looking at all of the remaining activities in this set of items that come after, which we call S sub k. S sub k refers to all the activities left after you've picked activity A sub k. So we're searching S sub k here each time through this loop, and k is going to change. So m is the index of where we're searching. So we start with the next activity 2, and we work our way up to the end. And so if the start time of the activity is after the finish time of the last one we picked, we add it to the set, and we update k to be that last one that we picked. So that would mean that S of k is now the subset, the smaller subset, after we put in activity of m went in there. So we're restricting ourselves to the remaining items. And you return A at the end. So we're going to trace the example here on this trace the algorithm on this example. I should have mentioned that S and F are arrays representing the start time and the finish time. That's why they're indexed as arrays here. So let's set n is 16, because we're not starting at 0 here. We're starting with activity 1. A is the set of activities that we're going to grow. It's initialized to be A sub 1, but some other ones will go in there. And we're going to set k is equal to 1. And then we're going to start with m is equal to 2. So if S of m is greater than or equal to f of k, so S of m is A sub 2. So far we have included A sub 1 here, so we've included this one, and we're looking at A sub 2 here. But its start time is not greater than the finish time, so we skip it and we go on to, I'll start using blue here, m is equal to 3. Now we look at A sub 3, and its start time, S of 3 is 4, and F of k is still 1, is 3, so that does count. So we add A sub 3 to the set here, and then we're going to increment k to be m, which is currently 3. So we'll change that into 3, and then we continue. M is going to be 4, but k is now 3, so the end time we're referencing against is 7, but k 4's start time is much earlier, so we skip out. We go to 5. The start time of S of m, which is this start time here, is not greater than f of k, which is this here, and so now we got to go to 6, and then here we got so now k is 8 and m is 9, and that doesn't work, and then we end. And by the way, I made an error up here. I guess you can see it now, and here really should be 9, the number of things in the set, 1 through 9 activities, not the amount of time we have available here. So that's how it works. Analysis of the runtime of this algorithm, of course, is very simple and straightforward. We have a loop running from 2 to n. N is the length of the activities, and everything else in here is constant time. Adding something to a set is straightforward as long as you're not ordering the set. So this whole thing, of course, is then going to be theta of n, with the possible additional time also needed to sort the activities if we didn't count that. So let's recap the greedy approach to solving problems. First of all, you need to know whether the problem you have is amenable to the greedy strategy. And if you don't know that, perhaps you might start with a dynamic programming analysis and then discover it along the way, as happened here. Or you might think about, well, what are some plausible greedy choices that we can make? So the first thing you want to do is consider how we can make a greedy choice. And these leave one subproblem to solve. Okay, then the next thing you need to do, of course, is prove that the greedy choice is always part of some optimal solution. So this is called the greedy choice property, which is that the greedy choice is always part of some optimal solution. Then the third step is to show optimal substructure. And in this respect, it's the same as dynamic programming. Both greedy algorithms and dynamic programming need you to demonstrate that an optimal solution to the problem contains within optimal solutions to subproblems. So how does all this proving things help you? Well, then you can see how you can write an algorithm that combines making the greedy choice with recursively solving the remaining subproblem to find an optimal solution to the remaining problem. So let's compare this to dynamic programming. Both dynamic programming and the greedy strategy require optimal substructure, but with dynamic programming, you tend to work bottom up. You tend to solve subproblems first, and because it's dealing with overlapping subproblems. Each choice made depends on knowing the optimal solutions to subproblems. That's why with dynamic programming we save things in the table, so then we can look at what the solutions with the subproblems were before we make a decision about how we're going to do the overall problem. We say if we divide the binary tree with this root, what's the cost? If we do it with this root, what's the cost? This one, what's the cost? Or if we do the matrix this way, what's the cost? This way, what's the cost? And so on. Let's pick the best. So we got to look at all those combinations of solutions. That's why dynamic programming works bottom up. The greedy strategy instead works top down. It simply makes a choice without having worked on the subproblems and then goes on to solve the subproblems. So in summary, dynamic programming and greedy algorithms both need optimal substructure. Dynamic programming works with overlapping subproblems and works bottom up. The greedy strategy, you have to show the greedy choice property, and it's going to work top down. So that concludes our example of greedy algorithms using activity scheduling with a lovely circular fern found on a trail near the Poli Poli area on Maui.